Hello and welcome to our lesson on the law of sines. So what the law of sines is going to allow us to do is to solve oblique triangles, but just a little recap. Um, we know that every triangle has 6 fundamental and unique properties. Every triangle has 3 unique sides, 3 unique angles. But if we're going to solve a triangle, meaning we need to find all 6 of those parts, we need to be given 3 of those components, 3 of those parts, and then we can find the remaining 3. So the 3 are specific to one of our congruence theorems or axioms. If a triangle is guaranteed, and just for a side note, in place of the word guaranteed, we sometimes say determined. If a triangle is determined or guaranteed by one of our 5 theorems, congruence theorems, then we can solve for the remaining 3 properties. They are guaranteed to be what they are in that triangle. We're guaranteed to all be solving for the same information. So we have a side theorem. If we're guaranteed 3 sides, then again the angles they're predetermined. We also have the side angle side. We have an angle side angle, an angle angle side, and then we have our right angle hypotenuse and side, or again sometimes we could call that just hypotenuse leg. So if we have a guaranteed triangle, if we have a triangle that's predetermined with the 3 pieces of information given in one of those theorems, again we can solve for the missing sides. Now if we have a right triangle, we have so many options for solving. We know that we can use Pythagorean theorem. If I have 2 sides, I can use that to find the third side. I can find angles or sides using trig ratios, so sine being a ratio of the opposite over the hypotenuse, cosine being a ratio of the adjacent side over the hypotenuse, and tangent being a ratio of the opposite over the adjacent. So we have that SOHCAHTOA we can use to solve. That's for solving angles and sides. And then we also have patterns in our 30, 60, 90 and 45, 45, 90 triangles that we can use to do some solving. So lots of options if we're looking at a right triangle. If we are not looking at a right triangle, so if the triangle does not have a right angle, remember we call that an oblique triangle. And oblique triangles can be classified in one of 2 ways. It could be that all of the angles are acute, so that oblique triangle would be acute, or one of the angles is obtuse, which would mean that oblique triangle is obtuse. If we want to solve, again, we still have to have a triangle guaranteed by one of our congruence theorems, but we can't use the same strategies for solving an oblique triangle that we use for a right triangle. The strategies we're going to use, or formulas we're going to use, will be either the law of sines, which is the one we're going to see today, or the law of cosines. And we will see that in our next topic. Okay? So before I just give you the formulas, I want to show you where the law of sines, where these formulas are coming from. And remember, obliques can be one of 2 cases, so I'm going to show you in both cases. I'm going to show you where does it come from, or how does it work if we have an oblique triangle that is acute, or if we have an oblique triangle that is obtuse. Okay, so either case, you're going to see the same thing unfold. So let's focus on this acute triangle for a second. Even though my sides aren't labeled, I know that across from angle A I will have side A, and across from angle C I will have side C, and across from angle B I will have side B. So let me stick those in there. And let's say I asked you to find the area of this triangle, just because I want to introduce a component. Do we know the formula for finding the area of a triangle? And you don't need to write this, but to find the area of a triangle, I hope we know that it's 1/2 times the base and height of that triangle. And depending on how the triangle is sitting, you could really call any one of the sides the base. Now, whatever side you choose for the base, then the height has to be perpendicular to that base. So when you're looking at a right triangle, the base and the height would have to be the legs of the right triangle because they are perpendicular to one another. They make a 90-degree angle. If you have an oblique triangle, it's not as clear what your base and height are. And actually, your base and height can change depending on what you want to call your base, or your height can change depending on what you want to call your base. But the same property has to be true in that the base and height have to be perpendicular. So let's say I wanted to find the height of this triangle. Now think if you were just measuring your own height. Generally you want to go from the top of your head down to the ground, right? Straight down to the ground. So let's call the base of this particular triangle this side here. Let's say this is our base. Okay? If that's the base, I would measure my height from the top of this triangle, this is at angle C, straight down to the bottom. So I would put this little dashed line in here, make it perpendicular to that base. That would represent the height of this triangle. Okay, and that should make sense. Again, if you how tall is this thing? Measure from the highest point there, C, down to the bottom, and we'll call that bottom like the ground. Alright, so that would be one way to measure the height. Now I could do the same thing from each of the angles, so I could flip the triangle around and measure a height from angle A. I can flip it around and measure a height from angle B, but right now I just want to focus on this one height. Okay, so let's say that I wanted to solve for that height, figure out what the height of this triangle was. Now I don't have any values here. That's okay. I can use an equation and come up with something that will help me solve anyway. So for instance here, let's say I wanted to include angle B in this right triangle. Okay, so I'm just going to focus on this for a second here. I could say that the sine of angle B is going to be equal to a ratio of the opposite side, which is over here, and I called it the height, over the hypotenuse, which I have labeled A, my little side A. So if I wrote that ratio, again, the sine for angle B would be equal to the opposite side, which I called H, and the hypotenuse of that highlighted triangle, which would be A. So H, in this case, if I wanted to solve for it, it's being divided by A, I would multiply by A, would be A times the sine of angle B. So now I have an expression I can use for the height. And now if I wanted to find the area of this triangle, I could multiply that 1/2 times my base length of C times my height, which is now A times the sine of B. Okay, side note. But what I want to show you is not that. I want to show you where we're going with this in terms of the law of sines. So now I want to turn your attention to the other triangle. Another right triangle that was created by introducing the height. So this triangle here. Okay, if I'm looking at now angle, I need another color. How about here? So angle A, for example, here. Again, just like I did with angle B, I could say that the sine for angle A is equal to a ratio in that right triangle of the opposite side, which is my H, over the hypotenuse now, which is B. So it would be H over B. So if I wanted to solve for H, again, it's being divided by B, so I would multiply it over. And so I could say that H is equal to B times the sine of A. So now, if you look, I'm saying H is equal to A times the sine of B, and I'm also saying H is equal to B times the sine of A. If both of those are equal to H, that means they have to be equal to one another. It's the same height in that triangle. So now I could take this next step and say that A times the sine of B has to be equal to B times the sine of A. And then we're getting really close to our formula here. Let me just center this. Sorry, OCD. If I take this and let's say I wanted to divide this side by A and divide this side by A to make this go away, and then maybe I divide this side by B and this side by B to make this go away. So I divide both sides by A times B. Then I'm left with a ratio of the sine of B divided by B equal to the sine of A divided by A. And that is one part of our law of cosines. Now notice we had no values in this triangle, so we did this generically, which means no matter what A, B, and C are, this is going to hold true. So if I write a ratio of the sine of my angle B to its corresponding side length, the side length across from it, B, and again a ratio of the sine of A with its corresponding side length, little a, those two ratios would be the same. Now I chose to do this with a height from angle C, and notice my ratios include A and B here. If I go and do this from another one of my angles, then I would get a different set of ratios. Might be the sine of B and B, or the sine of A and A, or it could also be the sine of C corresponding with side length C. So I could do this from any one of my angles and end up with all three of the ratios being equal. So the sine of B over B is going to be equal to the sine of A over A, and it's going to be equal to the sine of C over C. All three of them are equal. And so you see a lot of different versions of this. Again, if I picked a different corner, maybe I would get the sine of B over B equal to the sine of C over C. Or if I picked a different corner, then I might get the sine of, let's say, A over A equal to the sine of C over C, which means all of them are going to be equal. And so what we are going to see, get rid of all this mess, in our formula is a condensed version of all of that. So all of our ratios are going to be equal. If I write a ratio of my sine of my angle to its corresponding side length, all of those ratios in an oblique triangle are going to be equal. And remember, if numbers are equal, their reciprocals are equal, so we see these two alternative forms of the formula. So I can write the ratios with the sines of the angles on the top and the side lengths on the bottom, or vice versa, and they'll work the same way. Now note this is a condensed version of our formula. When we do solving, we're only going to be looking at two of the ratios at a time. So maybe it's those two, or maybe it's those two, or maybe it's the first one and the third one. So you're not going to do any solving with all three in there. This is just a condensed way to write this. Okay? Now, here, oh, I swear I erased those. Maybe I hit undo. In an oblique acute triangle, we saw how that kind of played out here. If I look at the obtuse, it's really no different. I can pick any angle to draw a height from. That means I would have to draw a perpendicular to the base that corresponds with it. So just as an example, let's say I wanted to draw a height in from B, just so you can see this a little bit differently. If I was to draw my height in here, again, straight to the base, the opposite side, I'd have to make perpendicular. So let's say this is the height here. Okay, then again, it creates these two right triangles. So let's say I wanted to focus on this right triangle, and I better label some sides here. Across from B, I have B. Across from C, I have C. And across from A, I have A. So if I focus on the yellow triangle that I've highlighted there, again, that becomes a right triangle. Then I could say here is my angle C. The sine of my angle C is equal to the opposite side, which is my height, over the hypotenuse in that triangle is A. So H is equal to the sine of C multiplied by A. So A times the sine of C. And then again, I could go to this triangle and do the same kind of thing. Let's say I'm looking at angle A. Okay, the sine of angle A would be equal to the opposite side over the hypotenuse in that green triangle, which would be H over C. And so if I multiply both sides by C, I see H equal to C times the sine of A. So just like we had a second ago, okay? If H is equal to A sine of C and H is equal to C sine of A, like if both of those expressions are equal to H, then they have to be equal to one another. So I could take this the next step and say A times the sine of C has to equal C times the sine of A. And again, if I took this side and divided by A, and this side and divided by A, these would cancel. And then if I divided this side by C and this side by C, then these would cancel, and I would be left with another part of my law of sines, a ratio of the sine of C over C equal to the sine of A over A. So all of these ratios, again, going to be equal. So here I have a sine of A over A, sine of B over B. Here I have sine of A over A equal to sine of C over C. Again, all three of those are going to be equal. Just kind of depends when you're trying to derive this, which is the work we were doing here, on from which angle you draw your height. Okay, so I could draw my height in from any angle as long as it's perpendicular to the base that's across from it. So Oh, sorry, mic went out. The law of sines, again, says that if we were to write ratios of the sines of each angle to their opposite sides, that those ratios would all be equal. Alright, so we can use this. Now, we'd only use two ratios at a time. Again, this is a condensed version of the formulas that you're seeing in the boxes here. You're not going to solve one equation with two equal signs in it. Okay, so you're going to pick two ratios, whatever applies to your problem, and you're going to solve. But there are going to be situations where this isn't going to be possible, and you'll see when we get to the next set of formulas in the next topic. But for now, we're going to be using these ratios to solve when the triangle is guaranteed by specifically two of our congruence theorems. So if we have an angle, angle, and side, or an angle, side, and angle, we're going to have to be given the two angles if I want to try to solve here. And it should sort of make sense. So just think about real quick if I was using just this little portion of the formula, okay? If I wanted to solve in this formula, generally when you use a formula, you can only have one unknown left in the formula. So like if I knew A and B, and let's say B here, then I could figure out my missing variable A. Or if I knew A and B here and A here, then I could solve and find B. But if I didn't know, and I think I just messed up when I said that, but let's say I knew A and I knew B. I don't know if I'm explaining. Okay, just go with me. So if I knew A, B, and then B, so little a, little b, and angle B, and I wanted to solve. Okay, yeah, no, I'm getting ahead of myself. I want to save that actually for the next topic. So just put a pause on that. I promise it's going to come back. Just go with me for now. Angle, angle, side, or angle, side, angle. Yeah, I'm getting ahead of myself. I'm going to try to put too much content in here because I saved that. I'm saving it for the next topic. Okay. So if our ratios of our sines of each angle, if I write ratios of the sines of each angle to their opposite sides, all of those ratios are going to be equal. And if you prefer the side length on the top or the side length on the bottom, it doesn't really matter. Just be consistent. So any ratio you write, sides on top, angles on bottom, or vice versa, angles on top, sides on bottom. What you don't want to do is flip any of them around. So you don't want to do one with a side length on the top and then one with an angle on the top. So just be consistent and you'll be fine. Okay, so let's try this. Let's try to use the law of sines to do some solving. For example, we're going to try to solve triangle ABC. Notice not a right triangle, just triangle ABC, given A is 38 degrees, B is 121 degrees, and side length A is 20 inches. So the first thing I would do is draw this out because it's not that hard to draw out a triangle, and it doesn't really matter what your triangle looks like as long as it has three sides. And we will label, can I move this? Yeah, and we will label. So again, it doesn't really matter. In a right triangle, C has to be the 90-degree angle, but here, it doesn't matter. So I'm going to call these, and my draw tool is still on. I'm going to call my angles A, B, and C, although again, doesn't matter where you label those. So angle A is 38 degrees. I'm going to put that in here. Angle B is 121 degrees. Obviously, my picture is not to scale because I have that in an acute angle and it's obtuse. It doesn't matter. And then I know side length A, which has to be opposite of angle A, is 20 inches. So I'm going to put that there. So we have to find one missing angle and two missing sides. Now the easiest place to start, I think, would be with angle C. So this angle wouldn't be too bad to find because we know the three angles in a triangle make 180. So if I want to find angle C, I'm going to take my 180 degrees total and subtract out the 38 degrees and the 121 degrees that are already there. And so with my calculator, so I don't goof this up, 180 minus 38 and minus 121 gives me 21 degrees left over for angle C. So now I have a 21 degree angle here. And that's an exact measurement. So moving forward, it would be totally fine to use that measurement. Okay, now if you were unsure about yourself and you thought somehow you might goof up subtracting and you chose not to use a calculator, maybe you don't want to use that measurement, but it should be fine, especially if you're verifying what you're doing, okay? Now, how do we find the next components? So let's say I wanted to find, I don't know, side length, let's go with B. If I want to find side length B, I have several options to do so. Okay, several options. So I have in my formula, my law of sines, it says if I wrote, stick with green, a ratio of the sine of angle B with its side length, side B, that's going to be equal to a ratio of any other pair, so the sine of any other angle with its corresponding side. So I don't want to use angle C yet because I don't know the side that's across from it. So I'm going to use the sine of angle A and its corresponding side A. So I'm going to have the sine of B, which is 121 degrees, over its side length. I don't know, so that's going to stay in as my variable. And that will be equal to the sine of A, which is 38 degrees, over the corresponding side length, A, which is 20 inches. And now I have everything I need to be able to solve. Right, I plugged in the 3 values that were known, and I have the 1 left that I can solve for. And when you're solving a proportion, cross multiply. So if I cross multiply here, I'm going to have B times the sine of 38. And if I cross multiply here, I'm going to have 20 times the sine of 121 degrees. And now, one more step. If I want to solve for B, it's being multiplied by the sine of 38. That means I have to divide the sine of 38 over. So my exact answer is 20 times the sine of 121 divided by the sine of 38. Again, that is my exact answer. I'm going to now go to my calculator to get an approximation for this. So just make sure your calculator's in degrees. So I'm going to make a fraction on the top of the fraction, 20 times the sine of 121, and then on the bottom, the sine of 38. And now I can see my side length, B. This is not what I had in my pre-work. Huh. B, so I'm looking at my, sorry, I worked this out, and what I have in my work is not looking like what I have here. Did I mess something up? 38, 20, 121 goes with, oh yeah, no. Yep, I sure did. I didn't mess anything up here, sorry. Just go with me. So 27.845, yeah, gosh, guys, sometimes I do not even know. Okay, so this all looks good. I am looking at the wrong picture in my completed. I worked this out to make sure everything was going to be fine before I start recording the video, and I'm looking at the wrong problem. Like, this is not what I got. Yeah, different problem. Okay, so you can see in the calculator this ends up being approximately 27 point, let's round to the hundreds place and call this 0.85. And the units here were inches, so we will say inches. Alright, so we found the missing angle, and now we have found one of our missing sides. So then the last piece would be to find the other missing side. So I have lots of options. I want to avoid using B because that's an approximation. So if I want to, let's say next, find side C, again, part of my formula says if I write a ratio for the sine of angle C to its corresponding side length C, it's got to be equal to sine of B over B or sine of A over A, but I don't want to use B because again I approximated that value. So I'm going to stick to the sine of A over A. So this looks very similar to what we did over here. So we're going to say the sine of angle C, which is 21 degrees, divided by its corresponding side length C, which is our unknown. That's going to be equal to, again, the sine of A was 38, and its corresponding side length was 20. So in the solving, we have basically what we have in the previous problem. The difference is instead of the sine of 121, it's the sine of 21, and instead of a B, it's a C. So if you wanted to jump to the solved form here, I could totally understand that. If not, I don't want to lose anybody here, I'll just cross multiply. So again, this gives me C times the sine of 38 degrees, and that's going to be equal to, when I cross multiply here, 20 times the sine of 21 degrees, and now to solve for C I have to divide. So C is going to be equal to 20 times excuse me, the sine of 21 degrees divided by the sine of 38 degrees. So the only thing that's changing from this version to this version is that angle, or because we're focused on a different angle. So into my calculator, I just need to change the 121 to 21, and then I get about 11.64. So we'll say side C is approximately 11.64 inches, and we have done it. We have found all of our missing components. So this triangle is solved. We've got all three angles, all three sides. Okay, now, again, I got a little excited, a little ahead of myself. I should have started by verifying that this triangle was guaranteed. So let me just go back to that. Never too late, right, to go back. If I look at the information I was given, it was an angle, and then an angle, and then we have a side. So I have two angles and a side, and notice the side that I'm given in this problem is not in between those two angles, not included. So this would be guaranteed, or we could say determined, by the angle-side theorem. So this would be a case where we're using the law of sines to solve in an angle-side situation. Okay? So let's look at the next one, and I will make sure to not look at incorrect work and have to pause for, I don't know, for you, it felt like an eternity. For me, like, I was just on silent there. And let's make sure we're guaranteed. So we're going to again try to solve it. Now, if you're feeling good, like you can do this, this would be a great place to pause the video and try this out. We're doing something similar here. Solving triangle ABC. We're given a couple of the angles. We're given one of the sides. Let's draw this out. Always good to try to organize your work. And remember, it doesn't matter how you draw your triangle. I just typically draw, I'm calling this a standard triangle, something that looks somewhat equilateral, although clearly our triangles aren't equilateral or equiangular, so they don't have equal sides, equal angles. And I usually just go ABC, although again, it does not matter where you put those, as long as you label the corresponding parts properly. So angle B is given to us as 82 degrees, I'll put that in there. Angle C is 24 degrees, I'm going to put that in there. And side A is 11 centimeters, so I'm going to put that across from side A. So if we look again at what we're given an angle, and a side. So just like the last one, two angles and a side. However, this time, the side is between those two angles. And so this means we have a triangle that is guaranteed or determined. Maybe I'll use the other word this time, just so you can kind of see that it doesn't really matter which word you want to use. We'll say guaranteed or determined by, in this case, angle, side, angle. So this would be an angle, side, angle case. Now I'm going to start it the same way. I know two of the angles. I can easily find the third angle by subtracting the two I know from 180. So I'm going to start there. Angle A is 180 degrees minus the 82 degrees and 24 degrees that are already in the picture. And so if I take 180 and subtract out the 82 and the 24, I'm left with 96 degrees for angle A. So again, my picture, not drawn to scale, because that should be bigger than 90, and it clearly isn't. That's okay. So I have all three of my angles. Hold on a second. I'm like, that doesn't feel right. Those angles are adding up to too much. And that's because I typed in a 2 and not 24. Goodness. I'm hoping you were screaming at me on the other side of this screen. 96. I'm like, no way. What did I say? The correct answer, 74. I swear I can use a calculator. Okay, 74 degrees. That feels better. 150. Yeah. Okay, so now I have all three of my angles. Let's proceed. Let's say I wanted to next find, I don't know, side length C. So remember, I can say that the sine of C over C has to be equal to, I can either say sine of A over A, or I can say the sine of B over B, but I don't know side B, so I'm going to use A with A. Take the sine of A over its corresponding side length A. So this would be the sine of 24 over our missing side C equal to the sine of 74, and I should be putting degrees in all these. Yep. Over the corresponding side length 11. And again, technically we're cross multiplying to solve, although after you do these for a while you can kind of skip some of this. So C times the sine of 74 degrees equal to, cross multiply here, we get 11 times the sine of 24. 11 times the sine of 24, and then to solve for C that's being multiplied by sine of 74, I divide. So C is going to be 11 sine of 24 divided by sine of 74. And now we're going to approximate that with our calculator. And I'm going to try to work smarter and not harder here. So let's put in 11 sine of 24 and sine of 74 and make sure we're still in degrees. Yep. And so C ends up being about 4.65, and what were the units? Centimeters. Okay, and now we're almost done. We have one more side length to find, and that's the side length B. And so sine of B divided by B, obviously I have to use that ratio to solve for B. It's going to be equal to, I could say sine of C over C or sine of A over A, but again, I don't want to use C because I approximated that value. So I'm going to stick with the sine of A over A. So sine of A over A. So this is going to look, again, just like the last one. I have the sine of B. B was 82. So the sine of 82 degrees divided by our missing side B equal to the same ratio we had over there in green. So that's the sine of 74, that's A, over A, which was 11. And again, if you wanted to skip to this part because you already know how this is going to work out, I'd be totally okay with that. If you don't want to because you need the practice, cross multiply. Then you have B times the sine of 74 degrees equal to the cross product here is, I swear I said go back to pink, 11 times the sine of 82, and then we divide to solve for B, divide over the sine of 74. So 11 sine of 82 divided by the sine of 74 is our exact answer, and we're going to go to the calculator to approximate. So 11 sine of this becomes an 82, and on the bottom we still have 74, so this is going to be about 11.33 centimeters. And again, we are done. So we were given the three properties we needed to guarantee or determine this triangle by angle, side, angle, and we were able to use the law of sines to find our two missing sides and subtract from 180 to find our missing angle. Okay, and that's the process. Basic solving until we get to what I was almost spoiling the surprise for earlier, something called the ambiguous case in our next topic, and then when we have the other congruence theorems determining triangles, we'll see why the law of cosines is going to be necessary. For now, I think you've got enough to get going on your homework, but as always, if you have questions, feel free to reach out. Until next time, take care.